Testing, testing. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. So today we're going to go over a list of fun problems involving double integrals that are typical of a multivariable calculus course. So the first one we're going to be taking a look at is to evaluate sine of x, sine of y on some region from 0 to pi and 0 to pi. So just expressing this as an integral, that's going to be sine of x, sine of y, dx, dy. 0 to pi, 0 to pi. It doesn't really matter which one comes first because, well, just from symmetry, but also because of Fubinis Law, Fubinis theorem, which lets you interchange the order of integration for nice functions pretty much at will, whatever's convenient. So I think the first pertinent thing to do is to maybe just take a look at what this actually looks like. Hang on a second. Let me just quickly change something. Let's see if I have it pulled up over here. Okay, so here we go. So, maybe can I just draw here? Okay, more or less. So the idea here is that if this is sine of x times sine of y. So if this is the x-axis, this is the y-axis. Hopefully you can see my pointer. It's not terribly big, but it should do the trick. And we're basically being asked to find the the volume under the surface, right? Basically the volume of a hill, right? Because single variable calculus, you sometimes get asked to find the area under a curve. Now for one dimension higher, it's going to be volume under a surface. So if we look at 0 to about pi, which is kind of like here for x, and 0 to pi for y, this is sort of saying we're trying to find the volume of like this little hump right here. You see that? Just this one thing. So what are we shooting to do? How are we going to do this? Well, it's a little bit tough to quote unquote like integrate things directly, so to speak, but Fubinis Law lets us break a very nice integral like this into sort of a product of two separate integrals, right? Because the x and the y behave really nicely here. They're not very entangled, so to speak. And I use that word very loosely and maybe intuitively. Because they're kind of not entangled, you can basically say that this is just equal to the integral of sine x dx times the integral of sine y dy from 0 to pi and 0 to pi. And hey, both of these, you can just maybe write some parentheses to just help you conceptualize it better. But each of these are integrals that you know how to do from, hopefully from Calculus 2. And at this point, well, all there is to say is this is going to give you some straight up number, and this is in fact going to give you the exact same number, because when x and y are sort of separated from each other, right, they both just become this dummy variable of integration. So these two things are, it should be clear that this is the exact same integral, just multiplied by itself. So just go ahead and calculate that out. So the lesson of this problem is basically when you're trying to calculate the double integral, it's kind of like the volume under the curve. Very hard to draw a hill, fortunately. But even though that seems kind of conceptually complicated, for problems like these where x and y are, again, I'm using the word loosely, untangled, like disentangled from each other, you can split them apart really, really nicely. And yeah, to just give you an example of something that's not quite as nice, you might have a situation where you have like sine of xy, which is just, let's see, if you're trying to take the double integral of this, right? This is not as nice to split up. This would be a little bit harder, and you'd have to think of something else, right? I don't have any clean way to split this up into two separate integrals, at least not off the top of my head. So that's not so nice. But this is super nice. Okay, so yeah, I'll leave the rest of that one to you. All right, so going onwards, I think our next problem looks something like, okay, so if we have some plot that looks like this, and we sort of have two, these are not quadratics, these are like fourth order curves. Doesn't really matter. So y to the fourth is equal to 1 plus x, and y to the fourth is equal to 1 minus x. Well, okay, the specific function doesn't matter too much, right? Let me, for the sake of just maybe changing up the problem a little bit, maybe let's say y squared is equal to 1 plus x and y squared is equal to 1 minus x. just to freshen things up a little bit. The curves look a tiny bit different, but like not that different, right? Quadratic is just not as flat in this area, but that doesn't really matter. So the idea behind this problem is basically asking you to say, okay, D is the region bounded between them, so that's D. And we're being asked to write d f of x comma y dA in two different ways, one with respect to x first and one where you have to evaluate with respect to y first. So the idea here is that dA is sort of equal to dx dy, or it could be equal to dy dx. And these equivalences are guaranteed only for nice functions according to Fubinis theorem, which I forget the conditions off the top of my head, but for multivariable calculus, any function you see is probably going to be nice. Yeah, unless of course the spirit of the problem is to present a nasty function for you. But for something like this, where we're just told to represent it with f of x comma y, I think it should be pretty reasonable to assume that they're talking about a function where Fubinis theorem applies. But the idea here is basically, if dA is just some like random infinitesimal tile, anywhere on the anywhere here, f of xy is kind of like saying, okay, that's how high above the page, or perhaps below the page, a hill is, and you're basically being asked to find the volume of that hill by doing this integral. Okay, so the idea here is that instead of doing dA, you could instead do a dx dy, right? And the idea here is, if you integrate with respect to dx first, that's sort of like saying, okay, that's basically figuring out the okay. If you're integrating with respect to dx first, that's basically saying, okay, for a fixed value of y, that's sort of the outer variable, so to speak, right? So if this was dx dy, that's basically saying, okay, fix y for a moment, just some value of y, and then basically just vary x for every possible one of these infinitesimal squares. And then if you figure out what, if your function f of x comma y, again, describes the height of maybe this hill, right? Each one of these little cubes kind of represents that tiny little area, that tiny little volume, rather, that sits with its base at one of these differential chunks. Hopefully that's reasonably easy to conceptualize. But the idea here is that, okay, we're going to so I don't know, how do you draw this? It's kind of like this column coming upwards, right? And the height is basically the hill. And then the height of the hill is basically f of xy. And then the little base at the bottom is dx, and the little base at the bottom is dy, right? So the idea is, if you add up all these like little differential columns, you sort of get the volume corresponding to this row, right? So that basically means you've integrated the dx first, and then now you're going to do this for every single y value, which means you're going to do this for every single value, for every single one of these sort of rows, so to speak. And then once you've done that, once you've added all those values up, that's basically your expression for the volume of the hill. So you can basically write this integral two separate ways, right? You can either do this with respect to x first, or you could do this with respect to y first, right? The way I gave this explanation, there's no reason why I couldn't have chosen it the other way, where you sort of do your tiles like this in a column-wise fashion, right? It's still going to be dx and dy. It's just that dy is sort of the first thing you think about varying, and then once you've gone through for all the values of all the different values of y, then you think about the next value of x, right? And then tessellate all the different possible columns. So yeah, dx dy is, or versus dy dx, is basically just saying, okay, which it's basically saying, like, how do I put it? Whatever variable is sort of innermost is the one that you're kind of is kind of like the most granular one, so to speak. Like over here, like over in this example, dx is innermost, And it corresponds to this case where you're sort of varying dx at the innermost level, right? And then once you vary at every single one of dx, then you start varying dy, the other rows. So like the dx is sort of the more granular one. Whereas over here, it's sort of like saying, well, x is fixed for a moment while you do all the different values of y. So y is sort of like your most granular variable, and that's why dy is sort of in the inside here, right? So this is the correspondence. But okay, now we've talked about that conceptually. So what do you actually have to do in terms of work for this problem? Well, it's really not that crazy. You basically just have to figure out what the bounds are, right? You have to figure out what the bounds are. And these aren't supposed to be zeros. These are supposed to be like fill in the blanks, right? You're supposed to come up with like concrete values for this stuff. And the only difficulty here is that, how do you put it? Let me clean this up a little bit. The difficulty here is that while your outer variable is really nice because you can just figure out let me reword that. The difficulty here is that if you're tessellating the x's first, right? If you're tessellating the, varying x first, the issue is that how far it goes in each side depends on y, right? Because at this particular fixed value of y, it goes pretty far. But up here, for this particular fixed value of y, it's a little bit wider, right? It's a little bit wider. Whereas down here, if for a particular fixed value of y, there is really not that much. You kind of see how for each fixed value of y, x could vary a lot or it could vary a little. You see what I mean? And that's basically the idea that we're getting at here, where, okay, that's basically the idea we're getting at here, where y squared is equal to 1 minus x and y squared is equal to 1 plus x. Well, how do I explain this? The idea is that you need to express how x goes from here to there using these given things, right? So what this means is you probably want to solve for x in terms of y. So if we try to solve for x in terms of y, we'd get x is equal to plus or minus y squared minus 1, right? And what that sort of means, let's erase this. What that sort of means is because, well, this was a quadratic, right? So there's sort of a positive component. Excuse me, there's sort of a, why am I doing this? It's a quadratic, so, or rather, when you invert a quadratic, you get a square root, and that's going to have a positive and negative component. So what this means is if this is the positive half and this is a negative half, right? And over here, this is, what does this turn into? X squared, or rather, x is equal to 1 minus y squared, or the square root of that. Yeah. Sorry, what am I getting mixed up right now? Hang on, there's so many messy things right now. Something's a little bit backwards, and I just need to pinpoint what. So this function right here is describing this curve, right? So if we solve for x in terms of y, yeah, what test does it fail? Oh gosh, let's see. So yeah, we want some function, let's call it x is equal to g of 1 of y, and x is equal to g2 of y. And we basically just got to figure out a way to express that x goes from here to here, right? So let me figure out which of these four things that... So we have basically we basically have four functions, right? X is equal to plus or minus 1 minus y squared, and x is equal to plus or minus y squared of y squared minus 1. So right now we just need to figure out what's what, and I'm having a hard time because I'm being an idiot. So, all right, let's just figure out some values, right? When y is equal to 0 here, sorry, when y is equal to 1, that's up here. And when y starts to did I solve for this wrong? What the heck is going on here? When y gets larger, when y gets smaller than 1. So how does this ride this way down, right? So as y gets smaller, well, I think I'm getting imaginary numbers. What's going on here? Y squared. I'm doing something very stupid. X is equal to 1 minus... X is equal to 1 minus y to the 4th? Uh-huh. X is equal to... Yeah, I'm an idiot. Why did I solve for it? Where did the square root come from? Ah, gosh. All right. So that was really stupid of me. I just had a total brain fart. So x is equal to square root of... Sorry, x is just equal to y squared minus 1. And x is equal to 1 minus y squared. That makes more sense. I was getting confused because the square root means an imaginary number. So, yeah. Okay, so now when y is equal to 1, we get this value over here. But if y is less than 1, if y is less than 1, we start going down this way, right? And x becomes negative because the negative 1 is larger than the y squared until y becomes 0 down here, in which case x is just negative 1. And then once y gets more and more negative, then x starts increasing again because of the square. Right? So, okay, that's good. So this is basically saying x is basically starting on the left-hand side over here, right, from the 1 minus y squared line, and it goes all the way over to the right, which is the y squared minus 1 line. And you can kind of see that, if you basically, these are your bounds right here. Yeah, these go into the, these are basically the G1 and the G2 that we're looking for in the bounds of the integral. And just, I really want you to understand what exactly is going on, right? So it's basically saying that as y varies, like this outer y varies, right, x sort of varies between the sorry, what I mean is when it varies, okay, now let's say that it gets locked into some particular height, right? Let's say y gets locked in for some particular height, then x just sort of goes across, starting at the left, which is 1 minus y squared, and goes to the right, which is y squared minus 1. And that's exactly what we mean by bounds, right? Like, x's bounds are in terms of y, because it, how far left or how far right it goes depends on what the current value of y is. That's the idea of bounds. So in order to actually like express this, right, you'd basically just plug these values in over here. And which one goes on top and which one goes on bottom? Well, because this is the positive direction and this is the negative direction, whichever one of these functions is larger or more positive goes on top. And conversely, whichever one is more negative goes on bottom. So hopefully that makes sense. Right. And then once you've figured out what the bounds are for x in terms of y, well, then you just got to figure out the bounds of y, which are simple because now the bounds for y are just straight up numbers, right? The bounds for y are basically from y going from here to y going up there. So just figure out exactly what those heights are. Wow, okay, I made that way too complicated. So every single time you do this, you got to just remember it a little bit. And it's been quite a while since I've dealt with multivariable integrals. All right, so now to do this in terms of dy and dx, yeah? In terms of dy and dx, well, instead of these horizontal lines, that's basically saying, well, now they sort of tend vertically. Yes? They tend vertically. And the idea here is that, well, instead of solving for x in terms of y, now we need y in terms of x. Yeah, because this is dy, and it's going to vary from y is equal to, I don't know, let's call it h1 of x to h2 of x. And, well, okay, let's just solve for that. That becomes y is equal to plus or minus 1 minus x, and y is equal to plus or minus 1 plus x. So what we're getting here is just a little bit funny. Because now for some fixed value of x, let's say for over here, right? Or the idea is that, well, y starts at the bottom here and goes all the way up, right? The bounds for y depend on x, depend on the curve. And why this is a little bit funny is because whereas before we had the left-hand and right-hand side involve one each of our given expressions, now we have a situation where going from bottom to top, we basically just somehow use this information twice, right? Because the top is this top curve, in this segment right here is, well, I guess it's actually this one. This top curve is, this top curve, what is this? It's square root of 1 plus x. Remember, because this is this curve, right? So the top part is square root of 1 plus x, and the bottom part is the minus 1 plus x, right? So it's basically this information right here is giving us these two. Which is to say that when you do the bounds, well, one of them is just h2 of x, and one of them is h1 of x. Yeah, so this is h2 of x, this is h1 of x. So it's kind of funny, but it's kind of like saying, well, the top is the positive version, the bottom is the negative version, and we don't use the other one at all for the left-hand side. But once you get over here, once you get to the other side, it changes. Once you get to the other side, now we suddenly need to start using this curve, which is, I think, y squared is equal to 1 minus x. Y squared is equal to 1 minus x, which, well, it's kind of a similar idea, right? It's got a positive and a negative component. The positive is this part up here, and the bottom is this part over here. And if it's sort of like subtending, right, if for a given x, y just starts to sort of vary up and down, you got to sort of express those bounds. So what's the big picture here? The big picture here is that in doing the left-hand side, you basically got the bounds have basically got to be expressed with this thing, and on the right-hand side, the bounds have got to be expressed by this thing, which is a little bit funny because if you're solving this for the first time, it's sort of like saying, well, what the heck? How do I express all this in terms of integrals? And the idea here is you actually got to break it up into separate integrals, right? This is basically saying f of x comma y dy dx, and f of x comma y dy comma dx. So the bounds for what did we say earlier? The bounds for, let's say the bounds for this left-hand side, we called that h2 of x and h1 of x, right? That was like the 1 plus x and the minus square root of 1 plus x. Well, over here, let's call this h3 of x, or sorry, let's call this h3 of x, this part right here, and this part is h4 of x. And that's 1 minus x and minus 1 minus x. Sorry, my handwriting's a little bit messy. Right, so basically the idea is if this is h1 of x going to h2 of x, you got to split it apart, right? Because this is h3 and this is h4. Like, how do I put this? Like, if you think back to your one-dimensional calculus days, there were times where you would have to split up an integral because the bounds were kind of like inconsistent, right? You have some like classic problems where in just one-dimensional calculus, if you wanted to like figure out the area under the curve of like of something that looked like this via calculus, right? You would figure out y is equal to you would have y is equal to f1 of x for this line, and y is equal to f2 of x. Gosh, what's going on with my handwriting today? f2 of x for this line. And you would sort of like integrate this part by integral of, let's call this 0, let's call this a, and let's call this b, right? You would go from 0 to a using f1 of x, and you would have to add that from a to b of f2 of x, right? You would have to split it apart. It's exactly the same idea here. Now it's just in more dimensions. You got to split it apart for dy dx, because for this particular set of bounds, when you're integrating with respect to y first and x last, right, it uses this information over here. How do I put it? It uses this plus or minus square root of 1 minus x on the left-hand side, or sorry, whichever one it is. The point is, the information over here uses this equation, whereas the bounds over here use that equation. And that's sort of why you've got to split them apart separately. Sorry, I'm making this way more complicated than it needs to be, but I'm hoping that the extra discussion is erring on the side of clarification. I don't know. Okay, so that's what these bounds are, right? And then as for the other bounds, which are the bounds for x, this part right here, well, you just got to figure that out yourself, right? Figure that out yourself by just saying, okay, what's the leftmost value of x and what's the rightmost value of x? And just figure out what those are from the graph or from the equations. So for problems like this, where you're talking about sort of like bounded regions, usually the inner integral has kind of complicated bounds because one of the variables is being bounded by the other. But then the outer bounds are kind of easier because you've already sort of done that simplification. Sorry, you've already done the complicated work of relating one variable to the other, and then you just got to put your final bounds out here. Yeah, this is sort of what makes multivariable integration harder than regular single variable, is because you've got to sort of figure out the interplay between the variables. But yeah, okay. Ooh. I probably should have prepared a little bit more for that question. I just sort of glossed over it and figured I was going to wing it. But yeah, I can't believe how long I was stuck on that confusion. So, oh gosh, sorry, I didn't realize that there were people asking comments in the YouTube. But you weren't given an equation on the inside. That's a really good question. You don't know anything about what this equation is, but you're kind of assuming that it's nice, right? And the idea here is that the bounds here, like, how do you put it? The bounds here have nothing to do with the equation given, because the equation given is sort of like the height. The equation given is sort of like the height, for lack of better analogy, right? The bounds here have nothing to do with height. The bounds are basically just given separately from the height. So yeah, I think that should hopefully answer your question, right? This is a little bit different from the single variable integration, where this is a little bit different from this particular problem where the bound and the height are kind of related. You see what I'm saying? So it's not necessarily a perfect analogy, right? Because here, how do you put it? Well, that's not true. The bounds are from 0 to a and from a to b. So actually, I take that back. Yeah, the bounds are unrelated to trying to find the bounds for x here are unrelated to the function, and similarly in the multivariable case, the bounds for y and x are unrelated to the actual f of xy that you're trying to find the volume under the surface of. So hopefully that clarifies. Gosh, I hope you all are watching this at 2x speed. I feel like my explanations are a lot less rambly if I can get someone to maybe talk to. Yeah, usually no one takes me up on it, but I prefer having someone to talk to because it sort of gives me more direction on my explanations. But okay, so we have one last problem for today, which is the integral of 1 over ln of y dy dx from e to the x to e and 0 to 1. So this problem actually took me a moment, and I thought about it in advance. So where do we get the equation we are taking the integral of? Okay, so for that previous problem, you basically don't. You're basically... The entire problem was sort of to... The spirit of the problem is that you can think about the bounds agnostic of the equation. It's not actually asking you to evaluate anything, right? It's basically just showing how to set up the integral without having to actually having to integrate it. So just leave it as f of xy. Yeah, just leave it as f of xy, and all the work they're asking you to do is to figure out what these bounds are. And for the second problem, realizing that you got to split up the bounds. So yeah, they don't give you the equation because the equation is agnostic of the bounds. Like similarly in the one-dimensional case, right? I could give you like two totally different looking curves. I could give you that and like this instead, right? Instead of just the simple slopes. And you could still set the integral up the same way, just labeling the first curve as f1 of x and f2 of x, right? But the integral is otherwise set up identically. Yeah. So 1 over ln of y dy dx. This is... So the first thing I thought to do was whether or not I could just integrate this directly. And it turns out that this is super nasty. This is one of those very special functions that pop up in number theory that have a bunch of theoretical properties and are... I don't know if it's like not integrate. I don't know if it's not integrable by elementary methods or if it's just really, really complicated. But it's just a terrible direction to go down to try to integrate this directly. Right? Because that's what you would hope you could do. Like, my first thought was hoping that I could just integrate 1 over ln of y dy directly and then plug in the bounds and then integrate again with respect to x. but it just doesn't work out so nicely. Instead, what we need to do is sort of play around with this a little bit and figure out what we're actually doing. So I'm just going to draw out, this is y is equal to e to the x, and this is y is equal to e. Yes, and I guess this is x is equal to 0 for posterity. And what this is asking us to do, like, let's first think about what's happening here, right? So this is the bounds, and f of x comma y, you can think of, again, as the height. I guess it's just f of y, right? F of y. So this is basically saying up here, if you can imagine this as like a hill with a certain like boundary, up here is very tall, very high, and down here is very, well, actually, that's not true. 1 over ln of y is just a little bit, is actually a little bit funny. Yeah, I actually don't know exactly what that looks like. I guess 1 over ln of y is kind of the other way around, right? But anyways, the point that I'm trying to make is that each like row sort of has a different height, but within each row the height is the same. Yeah. So like up here, I guess. Yeah. Up here, I guess, is when ln of y is equal to about 1. Whereas down here, ln of 1 over ln of y is equal to, I think some very negative number. Yeah, that's not necessarily the most important thing in the world to figure out what the actual heights are. But the point being is that this thing kind of describes a hill where each horizontal like row has some specified height, and row to row the height can kind of vary, but within each row it's the same. So what I'm essentially trying to do, the spirit of this, is that instead of expressing it as dy dx, let's see if we can express this somehow as dx dy. And this is going to require us to change the bounds a little bit, right? This is going to require us to change the bounds. So whereas y varied from e to the x to e, well, right, that's sort of like integrating this way in terms of columns. Now we want to integrate it in terms of rows. So the left-hand side, I said earlier, was just x is equal to 0. And the right-hand side is x is equal to ln of y, right? Because I'm just inverting this function. And that's very suspicious. X is equal to ln of y, right? X is equal to ln of y. There's a really nice symmetry with that compared to 1 over ln of y. You see what I'm saying? So, okay, we basically just plug this into the bounds here. So this is x is equal to 0 and x is equal to ln of y. And over here, the outer bounds are basically just, well, what is y going from? Y is going from 0 here to e up there. So at this point, I think this is pretty solvable. And it works out really, really nicely because, well, let's think about doing the integrals, the inner integral first and then the outer. Well, the integral of 1 over ln of y dx, you notice that 1 over ln of y does not actually depend on dx. So in fact, you can just sort of like lift it out of the first integral and place it just, sorry, I scrunch it up. 0 to e. You can basically just lift the 1 over ln of y out of the first integral. It's like a constant, right? This may as well be like a constant factor of like 2 or like pi or something. You could just lift it right out. So all that you got left with is x is equal to 0 and x is equal to ln of y times dx. And wait a minute, that's the easiest integral in the world, right? Because the integral from 0 to like, anything c of just dx, that's just equal to c, right? This is like, what this is saying is basically the area under the curve of just the constant 1 function, right? So if this is 0 and this is c, and this height right here is 1, this is basically just getting the area of that rectangle. You see what I'm saying? So for this particular case, right, so maybe I'll just go ahead and draw this out. 1 over ln of y. Well, for this particular case, you get x going from 0 to ln of y. So this entire thing becomes an well, what does it become? I'll let you finish off the rest. But yeah, hopefully that's enough to take care of it. Yeah, sorry about this one. I definitely should have taken a bit of a more look at how to explain this ahead of time, but I assumed I was just gonna wing it. I got stuck for the longest time because my eyes were just glossing over and realizing not realizing that I was inappropriately square rooting it when I was talking about the integral with x on the inside. So yeah, I if this was helpful, make sure to I'd be grateful if you liked and commented. But yeah, anyways, I think the most important problem for this one is the third one, because it shows how switching the bounds of integration can actually help you in like a really like kind of clever way, right? Because what this is basically saying is that whatever height one of these rows are, it just so happens that the width of the row perfectly cancels out with that height. And that makes it so that this integral ends up actually being really, really easy. So that's the idea behind the third problem. Yeah, for number 2, it's really not that bad. Explanation-wise, I just fumbled it up a little bit because I was losing my mind trying to figure out where that square root came from, when in reality I had just inserted it inappropriately as a typo. So that was just me being dumb. Okay, well, that's all for today. Like and comments if it's helpful.